like I said, the test is just going to be on the first half of chapter 15 that we covered, and the majority of chapter 16, except that one little section right at the end that we didn't go over. So any questions? Don't everybody speak at once. All right, well, then I will just kind of go over some sample concepts, some sample problems, just to make sure that you guys know and understand it. Chapter 15, I haven't done any of chapter 15 in person, so I just wanted to make sure that everybody was clear on the chapter 15 stuff. I'd sort of kind of glanced over my notes and looked at the stuff that I had an asterisk beside, which is, always if I put it beside a definition or a formula, that's something that you need to know. And so that particular chapter was about reaction rates that we focused on. And I did have a definition on there, and it was the definition of, well, let me give you the definition and see if someone can tell me what's it's the definition of. What is the study of chemical reaction rates? Does anyone know? You can type it in the chat window, or you can say it if you know it. So let me see, let me try adding some text. Okay, let's see if this works. Kinetics. Kinetics is the study of chemical reaction rates. All right. So make sure that you guys know that definition. That was maybe the only definition that I actually gave in this particular section. But that's what kinetics is. Let's see. Okay, no one responded to anything. So it's the study of chemical reaction rates. So I gave you some formulas for actually determining reaction rates. And let's see, how do I remove this guy? Sorry, clear all drawings. There we go. So I said the rate was this. Draw, there we go. I said that the rate was equal to the change in the concentration of a particular either product or reactant in the chemical equation over the change in time. And I said that the rate could either look like that, or the rate could look like this. The negative change in the concentration of a particular compound over the change in time. And because there's a negative sign in here, you guys should be able to tell me whether A is a product or a reactant. Who knows?
Is A a reactant?
A is a reactant, that's right. And the reason why, the way to think about that is because we want rate to always be positive. And so if you think about the concentration of the reactant, and this is before our equilibrium discussion, right? So in chapter 15, we're still thinking about those reactions that are weighted towards the product side. So everything's basically happening in the forward direction. And so if you have a reactant and you're looking at the concentration of that reactant, what's going to happen to the concentration once the reaction begins and as time goes on? Well, the reactant's going to be used up, right? And so the concentration of the reactant as time goes on is going to be less than it was at the beginning. And remember, anytime we talk about the change in something, we're taking the final value of whatever that is that we're looking at minus the beginning value of it. And so if the concentration of the reactant is a greater number at the beginning than it is later in time, then we're going to be taking a smaller number and we're going to be subtracting a bigger number for it. And so for a reactant, the change in concentration is going to be negative. And so for the rate equation, we put this negative sign in there so we can flip the sign back to be positive so that rate will always turn out to be negative. All right, so just keep that in mind. If it's got a negative sign in it, then it's going to be a reactant, right? And this is going to be a product here because there's no negative sign. All right, questions about that or about the rate equation in general? So let's see. So I had an example in the notes here that said, like if we were told, for example, for a particular reaction that the substance has a molarity of 1.3 molarity at 2 seconds, and then we look at the molarity again at 10 seconds, and we see, whoops, let's see, we look at it at in 10 seconds, and we find it to be 1.02 molarity. So this is at 10 seconds. Again, are we dealing with a reactant or a product? In a normal forward, a reaction that's weighted towards the product side.
That'd be a reactant.
It's a reactant, right? Because the concentration went down as time went on. And so then the equation, if we're going to calculate the rate for that, the equation we have to use has to be the one that has the negative sign in front of it. All right. So we say negative change in the concentration of whatever we don't know what the compound is, but over the change in T. So that's going to be negative. The concentration, the ending concentration, change in, you always start with the ending value. So the ending value was 1.02 minus the starting value, which was 1.3. All right, all of that over the change in time, which was 10 seconds at the end minus 2 seconds at the beginning. All right, so we get a value of, if we punch that in our calculator, we're going to get a positive value of 0.035. And then our units, I should have stuck the units in there. Our units are going to be molarity over seconds. Okay, so that's a basic usage of the rate equation. And well, let me to find the rate of a single substance. All right, the rate equation is a little more complex than that. But that, if I asked you about the rate of an individual substance in a chemical equation, this is the equation that you would use if it was a reactant. And of course, it would be positive if it was a product. Okay. Any other questions about the usage of that particular equation? Man, got a lively group here. This is like two classes, people from both classes. And, I was really hoping that the livelier class would show the less lively class how it's done. But, you guys are letting me down. And I'm just going to leave it up to you to figure out which class is the livelier class, right? Because now nobody's going to know. We've actually had comments from both classes at this point. So it's kind of 1-to-1. That's the score right now. All right, so let's talk about that was the individual rate of a substance. What about the rate equation? And we said the rate equation was this for an equation that, looks like this, where the smaller letters, the lowercase letters represent the number of moles, and the larger letters represent that particular compound. We could say that the rate for a particular reaction equals K times the concentration of A raised to the X power times the concentration of B raised to the Y power. All right, and so we call this the rate equation. And so notice when we're using that was terrible. When we're using the rate equation, we're only looking at the concentration of the reactants, right? And this value K is unique for each individual equation. I'll either have to give it to you, or the problem, like one of the problems we had in the book is you had to solve for K, figure out what K was for a particular equation if we knew the rate already. Who can tell me what X and Y represent?
That's the coefficient of the term, like for A. Yeah, it's like the lowercase a for the capital A.
That's a good guess, because that's been the case in other equations, but it's not in this one. That is the value that we use in chapter 16 when we're calculating, somebody help me out, I'm drawing a blank. When we're calculating capital K, which is the equilibrium constant, right? In this equation, X and Y represent the order, what we call the order. And there's no way for you to figure that out. I've got to give it to you, okay? So let's just do a quick example to kind of show you how that works. And I'll just do the one that's in the book since no one has a particular question. Just to make sure that you know how to do this. I think the one in the book does ask us to find K. Yep, this is example 15.1, but it says that the reaction below is a first order. Okay, let me write the reaction down. So here's the reaction that they give us: 2H2 plus 2NO yields 2H2O plus N2. Okay, that's the reaction they give us, and they tell us it's given that the reaction is first order with respect to H2. So that means that when we're talking about the concentration of H2, that it is to the first power. That's the order of H2 in this particular reaction. The reaction is second order with respect to NO. And so for NO, our power is going to be 2 because it's second order, it says, with respect to NO. When the concentration of H2 is 0.012 molarity, 0.012 molarity, and the concentration of NO is 0.045 molarity, when each of the reactants are at this concentration, they tell us that the rate is equal to 3.41 molarity per second. They tell us that's at 25 degrees. And what is the rate constant and overall order for this reaction? So we don't really need to know the 25-degree part. It's just that the temperature has an effect on the rate, and so this value here is only good at 25 degrees Celsius. But for the purpose of this particular problem, we don't care. So they ask us, what is the rate constant, which is this value right here, this lowercase k, that's the rate constant. What is the value of the rate constant? And what is the overall order for this reaction? So let's get the overall order out of the way first, because that's the simplest one. And we want to make sure we don't forget that as we're calculating K. So the overall order for this particular equation, does anybody know how we calculate the overall order?
You just add the order of both of them together?
Yeah, you just add the order of each of the reactants together. So this one was first order, the H2 was first order, and the NO was second order. So it's just 1 + 2 = 3, right? Super simple for the overall order. So don't forget to, if you have a problem like this, don't forget to include that answer in there, because actually I had forgotten on one of the problems that I did. I calculated K and totally forgot to do the overall order. So now we're going to calculate K. Well, what is K? K, per our equation up here, is the rate. Is going to be the rate divided by the concentration of H2, both of our reactants to the appropriate order. H2 to the first power, and then NO to the second power, right? Because that's the order of NO. So we're just going to punch in our numbers for that. Similar to the equilibrium constant, the value on the orders and the number of reactants is going to affect what our unit is. So the unit's not always going to be the same for K. So you got to pay attention to your units as you're doing this. 3.41 molarity over seconds. The concentration of H2 is 0.012. Make sure you put your units in there so we can keep track of the units. And then 0.045 molarity, and this one's going to be squared. Okay. So we punch that in our calculator, and the number that we get is 140,000. All right, that's what 3.41 divided by 0.012 times 0.045 is going to give us. But let's check out our units. So what do we have unit-wise? Well, we've got meters on the top. I'm sorry, not meters, molarity on the top. On the bottom, we've got this seconds that was right here, and that should really be a lowercase s. I kind of wrote it like a big S. Lowercase s, and meters, not meters, molarity times molarity squared. So molarity cubed on the bottom, all right? And so if we do that, if we kind of reduce it down, this number is going to, instead of a 3, is going to become a 2. And so our final answer is going to be 140,000 with a unit of 1 second molarity squared. And that is, okay, good. That is what they got in the book. I thought for a second they didn't. They reversed the order of it. They put molarity squared times seconds, but either one's fine. Questions about that problem? Did I lose anybody anywhere? Is anybody else as thankful as I am that we haven't had to do Zoom calls all year long? It's a very different experience, isn't it? All right. So that's, let's see, I think that's basically it. That's the gist of chapter 15, right? Chapter 15, we talked about, we did mention collision theory, and we talked about how it's not just enough for these compounds to collide as far as the reaction to occur. What do you actually have to have in order for the reaction to occur whenever these compounds collide? Is anybody copying stuff down? Because I don't want to erase this if you're still copying down.
No, we're good. We
Okay.
got it.
All right. So in order for, so collision theory says that you have to have an effective collision in order for a reaction to take place. All right. So there's a picture in the book that kind of on page 458 that sort of shows you an example of how carbon monoxide and nitrogen dioxide are combining together, and the result should be carbon dioxide and nitrogen monoxide. But if you don't have an effective collision, it won't always happen. So the molecules have to be oriented in such a way that whenever they collide with one another, that it'll make the compound that shows up on the product side. So that's just the basic thing you need to understand about collision theory. It just says that just because you put the compounds together doesn't mean that they're immediately going to react. They have to collide in the right way. And we just kind of made 3 brief statements that that I'd went over in the lecture, the video lecture that you watched, that said that there are things that will affect that reaction rate and make sure that that the reaction happens quicker. And basically, if the concentration of the reactants, there was 3 statements about the reaction rate is proportional to something. And the 3 things were: reaction rate is usually proportional to the concentration of the reactants. So if the concentration of the reactants is high, the reaction is generally gonna happen quicker because again, there's more opportunity for things to collide together. Also, reaction rate is usually proportional to the surface area over which the reaction can occur. So as surface area increases, so will the reaction rate. And they kind of had an example in the book where you had this solid antacid tablet, and if you left it in solid form, like a Tums, if you left it in solid form, it's not going to react as well as when you crush it up and you make the surface area of that solid bigger. And so that should sort of make sense to us. And then also, reaction rate is usually proportional to the temperature. And the way to think about that is if things are getting hotter and molecules are therefore moving faster, then you're going to have more collisions, and so the reaction will happen quicker. So just something to keep in mind as far as reaction rates go in collision theory in chapter number 15. All right, So let's move on to any questions about chapter 16 material. And then if not, I'm going to move on and talk about some stuff out of chapter 16. All right, chapter 16. See a couple of definitions from chapter 16. We have Le Chatelier's principle. Anybody brave enough to try to give us a quick, your version of Le Chatelier's principle? All right, bunch of chickens. It's still 1-to-1 because Joshua's statement, well, wait a minute. No, it's one. Joshua, your statement was incorrect. So it's kind of, but I don't count off for that. You participated. So we're at 2-to-2 now. Okay. As far as the liveliest class. What is it?
Okay, so Le Chatelier's principle is when there's stress in an equilibrium, the concentration moves away from where the stress was.
Okay. All right. Good. Now, so the second class is up, guys. 3-to-2 now. That's exactly right. The equilibrium is going to shift in an equilibrium reaction. When the equilibrium is stressed, it's going to shift in such a way to try and relieve that stress. All right. So that's what Le Chatelier's principle is all about. We learned some things that will affect how the equilibrium is going to shift. And one of the things we learned about was temperature. That temperature affects Le Chatelier's principle. Who can tell me what happens if temperature goes up? Which way is a equilibrium reaction going to shift if temperature goes up?
Does it go towards the products?
That depends. What are we looking at if we're talking about temperature and how it affects a chemical equilibrium? We've got to take something into account for that chemical reaction. So you may know what it is.
It will shift away from the side that contains energy.
We're looking at the energy, right? So energy is, remember, change in H. So when we talk about change in H, we said that if change in H is negative, then which side is the energy going to be on in the chemical equation?
If it's negative, wouldn't it be on the product side?
That's right. Energy is on the product side. All right. So the opposite is true. Obviously, if it's positive, it's going to be on the reactant side. So if temperature were to go up, the equilibrium shifts towards the side, shifts away from the side that has the energy. So if in the case of change in H being negative, if temperature went up, that's kind of like the concentration of the energy going up. And remember, it always shifts away where the concentration increases. So it's going to shift to the reactant side if change in H is negative. If change in H is positive, then it's going to shift towards the product side. Because again, it's trying to get away from it's trying to shift away from where the energy is in the equation. All right, so that's the thing to remember with that. Of course, the opposite is true if temperature goes down. If change in H was negative like this and temperature went down, which way would the reaction shift?
Towards the side that the energy goes down on.
That's exactly right. It shifts towards the side with the energy. So it's going to, if temperature goes down, then it's going to shift towards the products in the case of this one. All right. And then the other thing that we looked at that was related to Le Chatelier's principle was pressure, how pressure affects equilibrium. And we said that it's only relevant whenever you're dealing with substances in which phase in the equation?
In the gas phase?
In the gas phase, that's right. So only gases are affected by pressure. If you don't have any gases in the equation, nothing, the equilibrium is not going to change. The concentration is not going to change for anything. So if the pressure goes up, which way is the equilibrium going to shift? As far, if you have, let's say you have more gas molecules on the product side and the pressure goes up.
then it'll shift towards the reactant side. 'Cause
Shifts towards the reactants. That's exactly right. It shifts away from where the majority of the gas molecules are. And so the way to think about this, if you think about it as concentration each time, right? In the case of temperature, when temperature goes up, it's going to shift away from where that. When temperature goes up, it's like the concentration of the energy going up. And Le Chatillier's principle says it's always going to shift away where that increase in concentration happens. Likewise, if pressure goes up, that's going to affect the gas molecules, whatever side they're on, the majority of the gas molecules the most. So think of that as like the concentration going up on that side because pressure increases. So it's going to shift away to the other side. So that's kind of, in my mind, the best way to sort of, think through those. If you kind of always connect it back to concentration, then you'll be good, right? Does anybody need me to talk through that again, or did I say something that just confused you? I don't want you to leave confused. I'm trying to help you think about those, how temperature and pressure affect it, but just want to make sure it makes sense to everybody. All right, tell me this. What about, okay, what does capital K represent?
Is it temperature?
Nope. That is our unit for Kelvin, but it's a variable in our equilibrium chapter that represents the equilibrium constant. All right, so capital K is the equilibrium constant. If K is equal to 1, what does that tell us about our reaction?
It's at equilibrium?
It's at equilibrium. That's exactly right. If K is equal to 1, then it's at equilibrium. What if K is greater? Well, before I answer that question, let me just refresh your memory as to what the equilibrium constant is. Why did I do that? So if we had something like we had before, and Joshua, I think this is what you were thinking about when I asked you about I did it again, when I asked you about the, what those exponents represented. Remember, K is calculated as the products are on top here. So concentration of C raised to the little c power times the concentration of D raised to the little d power over the concentration of A raised to the little a power times the concentration of B raised to the little b power, right? So that's our equation for K. So if this is the products, right, that's products there, and we've got reactants on the bottom. Then if K is greater than 1, which side is the reaction weighted towards?
The products.
The product side, that's right. This number here is biggest, right? The products number is the largest because K is greater than 1. And so obviously if K is less than 1, then it's going to be weighted towards the reactant side. All right, so make sure you understand that. And that's just understanding how the equilibrium constant equation is set up, right? Weighted towards reactants. All right, because you're going to have some just general questions on the test that have to do with, understanding that. Let's see. So, so if I give you a chemical equation and I say something like, if I give you a value for K, all right. So let's say, for example, let's say I was to give you a chemical equation like this. All right. And I said it's an equilibrium equation. And I said that K for this equation is really small, right? It's like 8 times 10 to the negative 7, all right? What would you, and I said, if this reaction can be drawn with a single arrow, tell me what the single arrow should be. Can this reaction be drawn with a single arrow?
Yes, and it would be towards the reactants.
Towards the reactants, right. So when K is really small, and when we said really small is on the order of 1 times 10, whoops, not 16, 1 times 10 to the negative 6, right? So when K is kind of on this level, less than or equal to that, then we can assume that the reaction is basically only going in the reverse direction, in the towards the reactant. So we could write it like this, right? Conversely, if I were to give you one that was a really large K, greater than or equal to 1 times 10 to the 6th, you could say that the reaction was going only towards the products. Okay, it's heavily weighted towards the product side. So make sure that you understand that as well. Let's see. So we talked about equations, you know, that you should just be able to look at a chemical equilibrium and kind of tell me what happens as the concentration of certain compounds in the reaction change. So let me just pick in one randomly from the book here. 2NO as a gas plus 2H2 as a gas. All right. And we say N2, wrote that kind of low, N2 as a gas plus 2H2O as a gas. Now, the first thing we notice is that all of these are gases. So that means all of them figure into these equilibrium discussions, right? What two phases do we ignore in our equilibrium discussion?
Solid and liquid.
Say that again.
Solid and liquid.
Solid and liquid, exactly. For some reason, it sounded like you said autumn and liquid, and I was, you know, I didn't need seasons of the year, so I was very confused, Cruz. But yes, you're right. Solid and liquid. Sorry, apologize for my bad hearing. All right, so let's say this reaction here is at equilibrium, but then all of a sudden we add more NO, right? So the concentration of NO goes up. What's going to happen to the reaction per Le Chatelier's principle? Which way is it going to shift?
The concentration on the product side is gonna get greater.
That's right. So this thing's going to shift in this direction. It's going to try to go away from where the concentration increased, right? So that means both the concentration of N2 is going to go up and the concentration of H2O is going to go up. And the concentration of H2, what's going to happen to that? It's going to go down, right? Because it shifted in that direction. Does that make sense to everybody? All right. Delete that. Let's make sure we understand this. What if I said what if I take away some H2? So if I take away H2, the concentration of H2 goes down. Which way is my reaction going to shift?
Towards the reactants.
That's exactly right. So it shifts back in this direction. So now concentration of NO is going to go up. The concentration of everything on this side is going to go down, right? Is that clear to everyone? Now, like I said before, if I had made this, let's say we made this to be, if we made this liquid hydrogen, and I said, I removed some of the liquid or I added more, what would happen to the concentration of everything else? You would say nothing, right? Because it's a liquid and it doesn't affect it. So just make sure you remember that. Let's see. See if I can see anything else here that I want to make sure that you know. Here's one. How about this? What if we have a problem like this? All right. And let's say that I know that the equilibrium constant for the reaction, we're given that the equilibrium constant for the reaction is 0.026 molarity, okay? What is the concentration of SO2? Do you have enough information to know what the concentration of SO2 is?
Yes.
You do. Wow. Joshy thinks that you do. He's going out on a limb here. That's huge. Hope that limb doesn't break on you, buddy. Let's see. K, how do we figure out K for this particular reaction? We have to take the concentration of the products first, right? And raise it to the power of the coefficient in front of those products. So it would look like this then. Does that look right?
Well, you wouldn't count the BAO because it's
Oh, that's what's going on here. So I wouldn't count this. And okay, that's a good point. Why wouldn't I count that, Joshua?
because it's a solid.
Because it's a solid. So what goes on the bottom of my equation?
Nothing.
Nothing, right? Because we don't include solids in there either. So it's just like K is just the concentration of SO2 over 1. So if the concentration of SO2 over 1 is equal to 0.026, then what's the concentration of SO2 equal to? It's equal to 0.026, right? So the reason that worked is because we weren't supposed to figure the solids. That's what you were supposed to catch with that problem. So don't forget that when you're calculating K, don't include solids or liquids in that. And anytime you're trying to figure out stuff related to Le Chatelier's principle and which way the reaction is going to shift, if it's a solid or a liquid that we're talking about, you ignore those and don't include those. If the amount of those are adjusted in the equation, it will not affect the equation. Okay. Just one more thing, I guess. Want to make sure that everybody understands the, if we have these drawings, so with the reaction rate. So if I had to draw and gave you a drawing like this, and let's say that 1, 2, 3, 4, 5, 6, 7, 8, 9. Those last two marks are kind of bad. That's a little close, sorry. All right, and we'll just say that each of these are 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220, 240, and 260. All right, so that's the time. That's time. And S, this is the reaction rate. Is this axis over here? And if I asked you at which point does this reaction reach equilibrium, what would you tell me? Roughly.
80.
Would that be like shortly after 80 seconds?
Yeah, so I drew it a little bit off, but yeah, 80 seconds. If you wrote down 80 seconds, I'd give credit for that, right? Because I was trying to line it up. I just did a poor job of lining it up. So basically 80 seconds, all right? If you estimated 82, 85, something like that, I'd give you credit for that. But 80 seconds is when this reaction reaches equilibrium. If we stressed the system at this point, because we added more of one of the reactants or something like that, right? And that happened to it. Obviously, if I gave you an equation, if I gave you a graph like this, and I said at which point is the reaction stressed, what time would you give me? At what time was the reaction stressed?
At 160 seconds.
160 seconds, that's right. So because everything kind of jumped up right at that point there. And then at which point does the reaction reach chemical equilibrium the second time?
About 190.
About 190, somewhere around there.
Yeah.
185, something like that, right? So again, I didn't draw it very well, but yeah, we probably would say this one was round 85 would be a more accurate answer for that first one. At 160, it was stressed, and then at 185, it reached chemical equilibrium again. Okay, so just make sure that you understand how to read those graphs. Remember, this portion of it here represents the forward reaction, this represents the reverse reaction, and this represents equilibrium. And then at the point it's stressed, again, this is the new forward reaction, right? Once it's stressed, this is reverse. I'm sorry. Yeah, reverse. And this is the new equilibrium after we stress it. Okay? All right. That's pretty close to being everything that I wanted to go over. I guess one other thing that you had on, the other thing you had on some of these homework problems is that, you know, they might give you a bunch of, they might tell you the K. So maybe they say K for a particular reaction is 0.345 molarity, okay? And then they give you a chemical equation and they tell you what the concentrations of the chemical equation is, you know, maybe at 8 seconds, something like that, the concentration of all the different products and reactants. And so they ask the question, is the reaction at chemical equilibrium? And if it's not, which way does the reaction need to shift in order to reach chemical equilibrium? And so, you know, we could have an equation and give you all the values for the concentration at a particular point in time, and you could calculate K. And so let's say you calculated K and you got a value like 0.67 molarity. And so if that's the K that you calculated, is the reaction at chemical equilibrium? If this is chemical equilibrium, clearly it's not, right? Because those numbers aren't the same. So the number, so K is too big or too small?
Too small.
It's too small?
Oh, wait, no, too big.
It's too big, right? 0.67 is bigger than 0.35. So it's too big, so it needs to get smaller in order to reach chemical equilibrium. So since K has to do with the concentration of products over the concentration of reactants, if K is too big when we calculated it, then which of these numbers has to be, which one has to be too big in our K equation? If K is bigger than it needs to be, the top or the bottom part of the fraction is too big.
The top is too big.
The top's too big, right? So we need the top to get smaller. We need the bottom to get bigger. And so what we want this reaction to do is we want it to shift towards the reactants in order to reach equilibrium. Everybody follow the logic that I went through to kind of figure that out? So I think that's it, guys. I think if you understood all those concepts, you get those definitions, and you know how to do those types of problems, I think you'll do great on the test. I know some of you don't test well in person, especially since I'm such a mean teacher, and you know you're probably really nervous being around me. I understand that. So it's going to be tough. You know, there's going to be all kinds of scary things there, like chocolate and different types of candy and donuts and things like that. So it's going to be rough. But I think you guys can do it. Like I said, if you just focus on the material and try not to stare into my scary eyes, right? You'll be all right. So nothing else? Nobody has? Let me make sure nobody sent a problem after the fact. Nope, I don't see
I do have
anything.
an example that I was wondering if you can go over.
Which one?
So first off, is 16.5 going to be on the test?
16.5.
Mhm.
What are we talking about? Is that,
It's-
you talking about that example?
Yes.
Okay, let me see.
Sorry.
That's okay. $16.5, yes. Yes, that type of problem should be on there. Example 16.5, right?
Yes.
Yep, okay. So you want me to go over that real quick?
If we can, yes.
Yeah, sure. All right, so 16.5, it gives us an equation like this. Whoops. This is so much easier than when I tried to do it last year with just a mouse. Can't believe I should have invested in one of these a long time ago. All right. So that's the equation that it gives us. And it says this is the equation that everything reaches equilibrium. But what will happen to the concentration of H plus? So they're interested in the concentration of H plus when more Cu plus is added. So if we add Cu plus, that means that the concentration of Cu plus goes up. So something on the first thing we need to see, this is the first thing you need to do when you look at an equation like this and it has to do with equilibrium, identify the substances in the equation that don't matter. Which substances don't matter?
The solids and liquids.
The solids and liquids don't matter. So sulfur can be taken out, H2O can be taken out, copper can be taken out. I think that's it. So everything else is aqueous. Aqueous and gases all count, right? So if Cu plus goes up, the concentration on this side goes up. Le Chatelier's principle says it's going to shift away where you have the concentration increasing. So it's going to shift in that direction. And so that's going to force the concentration of H plus to increase, all right? Does that make sense, Cruz?
If I believe so.
You think so?
Mhm.
So whatever side concentration goes up on, just remember it shifts away from that. And since it shifts away, then it starts making everything more of whatever's on the side that it's shifting to. You know, if they'd asked us about H2SO3, that concentration would have also gone up on this side because it shifted towards the products. Okay.
And if it went up on the product side, would that decrease the reactant side?
If it went up on the product side, what now?
Like if let's say H plus one had an increase in concentration, would that have a decrease in concentration for the product side? I mean, for the reactant side?
Well, let's see. So just to make sure I'm following what you're saying, we had the equation at equilibrium and we decided to increase the concentration of H plus, correct?
Right.
All right. So if it increased over here, which way is the reaction going to shift? It shifts away from the side that the increase is on. So the increase was on the product side and it shifts away from the product. So it's going to shift towards the reactants. Okay. And so that means everything that this arrow is pointing to is going to go up. So Cu plus goes up. Everything is pointing away from, except for the one that was directly affected, you know, that we messed with to start with. Everything it goes away from is going to decrease. Make sense? Okay. All right. So what will happen if H2SO is removed? That was the second question. So we removed H2SO and they wanted to know what happened to H plus if we removed H2SO. So the concentration of H2SO goes down. Which way does the concentration shift? H2S, is it H2SO? Yeah, H2SO3. So the concentration of H2SO3 went down.
It'll shift towards the product side.
It shifts towards the product. So it's going to go, if it decreases, it's going to go towards the decrease. So it shifts this way. So that's going to make more H plus because the arrow is pointing in that direction. If they had asked us about Cu plus, concentration of this is going to go down. And then the last question they ask is what will happen to the concentration of H plus if more S is added? We said S doesn't figure in this at all because it's a solid. So in that case, nothing would happen to the concentration of H plus in that case. If we added more solid. All right. So Any other questions? Everybody clear? Thank you guys for participating. I think yeah, I think it was pretty even overall, actually. I don't know that one, I kind of lost count because you guys began to participate. So nice job. Each of you, you know, you got neither class is having to leave with their head hung low. Well, let me see just a second. Actually, though, if I look at the number of people from each class that participated, I might have to go with, well, see, here's what I don't know. Did Joey and Jerry comment, or was it just one or the other? I have no idea because they're on the call together.
Our voices sound the same though, so you couldn't really tell.
But it was both of us.
It was both. Okay. I think if both of them participated, then I think the second class may have beat you guys in the first class just slightly. So, so the competition is on. We'll just have to see who can have the best average on the final exam, right? That'll be the final blow there. That you guys in the second class can nail the lid down on their coffin if you guys can beat them out average wise. All right. All right, that's it, guys. That's good. That was about an hour. That's what I was hoping to do. Joshua says y'all are going down. All right, the game is afoot. So, you know, I told you guys in class Thursday that we will have about 30 minutes before we take the exam, if we need it. If we don't need it, if there aren't any questions, we'll just go ahead and start the exam. But we will have about 30 minutes to answer some questions before the test starts. So come prepared, you know, for 4 questions because I know you guys haven't probably finished your homework yet. So if you've got more, if you're still working on homework and you run into some additional questions as you're going through that, we'll have some time to answer that before we take the test on Thursday. Okay. Lily says you're not going down without a fight. I like it. All right. So, oh, and by the way, I've got 2 markers that are out of ink. So there's one final chance for each class to get a +1 if I can ring the trash can. So we'll see how that goes. All right, guys, y'all enjoy the rest of your day, and I will talk to you later, Lord willing.